All right, so we start with Alexandre, and then all the others are coming right after that, okay? So I will show the slides, and then you can go on. Alexandre.
Okay, thank you. Okay, thank you. Hi, my name is Alexandre Magno. I am a PhD student of UFES, of Espírito Santo. And here I'm going to do a little bit of an abstract of my work that I was working with my advisor, Professor Jaziel Goulart. You can see in my poster, sorry for the blank slide, I did it on my tablet. But anyway, what he proposed to me that we work with breaking index in pulsars. Breaking index, he proposed to me that we use breaking index as a way to uh, know emission models, to discard emission models. Anyway, what is the breaking index? You see, pulsars they spin very fast, and they slow down over time, and they slow down very slowly. And a way to quantify this slowdown is by the breaking index. That's the N over there. In this table, we have 9 breaking index measure. We have over 3,000 pulsars. Only 9 we can measure the breaking index because it's very difficult. We have to know the first derivative of the period and the second derivative to know the breaking index. And the main thing is, if you go to any textbook of astrophysics, you will see that the breaking index is 3. They have a model for the breaking index is 3. It's the MDR model. The values that we observe are far away from this model, so we have to search for another way to measure, or another way to consider, another model to consider. So the model that I'm considering is the pulsar wind model. Yeah, the energy lost by the star is for the MDR model, which stands for magnetic dipole radiation. There is radiation comes from the star, and there's a lot of things to pack over here. I'm just trying to simplify everything, but in the main thing, the pulsar wind is the wind around the pulsar, and the pulsar have this magnetosphere, which is where the wind blows, if you say so. And we have some models of emission in this magnetosphere. These models of emission there are many. Some of those are in this table. And we can see that this acceleration happens in gaps. And this acceleration also, this acceleration of particles generates radiation, gamma rays and radio waves and everything else. And can you pass, please? Sorry. Okay, that's. If you want to know more, please talk to me on my poster. I'll be happy to explain with fancy words. Thank you.
Okay, thanks, Alexandre. Now, Amir Farzan.
Hi, thank you for the time. Very briefly, as Alicia was talking about the electromagnetic cascade, we know that at the ultra high energy regime, when the energies are very large, basically the electron pair production and the inverse Compton scattering are not the only interactions that can happen to the photon-photon and electron-photon interactions. Two of the most important interaction channels that can happen is the muon pair production and double pair production, as you can see here. And then if you calculate basically the effect of the muon pair production and double pair production in the cascade with the Monte Carlo simulation, you will see that the non-negligible fraction of the energy, a non-negligible fraction of the energy is going to neutrinos, around 24% of the initial energetics. And this is important for us because we can probe the high redshift universe, which is mysterious for us. Then we can we calculated the neutrino spectrum, and you will see 1 to 2 orders of magnitude is higher than the conventional scenario, which is the pion decay. And yeah, that's it. We can basically probe this spectrum with the grant, which will be constructed up to 2030. And yeah, and the future works is also to calculate all the other microphysics, which we are doing. I will be here if you want to ask any question. Thanks.
Okay, hello everyone. My name is Hania, and in this work we have developed a method to measure the baryonic acoustic oscillations, the angle scale, without using a cosmologic model. Okay, almost independent of this. So this is the. Can you? That's it. Okay. Can you go to the second slide, please? Yeah. So the idea is quite simple. Instead of calculate the distance of the galaxies, which requires a cosmologic model to a priori, we have calculated the angular correlation function of these galaxies inside of a redshift beam. But using this estimator, which just compare the statistics of a real catalog with a random catalog. Okay, so then when we calculate this estimator for each redshift beam, and then we infer the parameters of this phenomenological model where the position of the baryonic acoustic oscillations peak is going to be the peak of this Gaussian. Okay, of course there are some biases in this method, like these three main biases. We have studied them. We have studied how they behave and how to correct them. Okay, I don't have time to explain them here, but if you want to know, I can explain better in the poster presentation. And we got this data set here. In blue is the measurements that we got. In yellow is the measurements of another group with a similar approach. And in gray is the predictions by the best fit found by the Planck 2018. Okay. Can you pass, please? So as the main result of our work is our measurements, and then you can use this to constrain parameters of cosmological model. Like here we have some examples of lambda CDM, but you can use you can use them to do different path analysis. Yeah, I think that's it. I can explain better in the posters.
When people finish early, like Amir Farzan and Hanier, we have time for questions. If anybody wants to ask questions for them, actually, because they finished a bit early. Okay. Okay.
How did you manage to get the error region, the error associated to your points so small? Because if I understand correctly, your work is an improvement in respect with the other one because it's closer to the fit. Is it true? How did you manage to get the small error bar?
we have used more catalogs than the first, the other measurement in yellow. So we got covariance metrics more with diagonal is smaller. So we got better inference in these parameters of the phenological model as well. But I'm not sure why exactly we got better constraints here. Maybe because we have used more data set, more catalogs to get this. So the statistics decrease the error bar so simply.
Great. Thank you.
Hi everyone, my name is Arthur, and I'm going to briefly present here my master's project, which is entitled Cosmological Constraints Using the Integrated Saxwell Effect. So, briefly explaining what is this effect, specifically the late integrated Saxwell effect, which is what I'm focusing on my project. Basically, it's a result of the transition between a matter-dominated universe and the current dark energy dominated universe. What happens during this transition is that, as you can see here, what's the button here? Okay, no, go back at the laser point. It's this here. Okay. So as you can see here, during this transition, the tendency is that these gravitational wells flatten. So we can imagine that, for instance, CMB photons passing through these wells, they enter with a blue shift during this descent, let's say, and when they come out, the red shift that they suffer when they come out of this well does not compensate for the previous blue shift because of the dynamics of the wells. So that leaves a net blue shift which we can measure with CMB temperature maps. And we already know very well how this presents itself in autocorrelation spectrum for the CMB temperature map. But one can imagine that because of this relation between gravitational wells and the CMB photons, we can probably measure a cross-correlation spectrum. So that's the focus of my project, is to understand this effect from this point of view. Here are a few calculations. I'm not going to go into the details, but basically what this is doing is calculating the cross-correlation spectrum, and the predicted result is something like this. This result is predicted for a specific galaxy catalog called the 2MASS, but there are problems with analyzing the real data because this data is usually dominated by cosmic variance, so there are many details that I can cover in much more detail in my poster, so I hope you can visit.
Okay, thank you, Arthur. Now, Carlos.
Thank you. Hi again. Well, my name is Carlos Cruz, and as I said in the first day, I'm really interested in cosmic rays, and perhaps after this presentation, you will see that I'm more interested in muons. 2 months ago, I was assigned to this project, so it's basically a application for cosmic rays, and it's an image technique that's called muonography. The idea is to take advantage of all these characteristics of muons, basically their high penetrating power, and to measure them, their flux, so we can get an estimate of the material that is transversing. And we can imagine this in really big, massive structures. See? Just a picture to understand how this works, and obviously in high energies, most of the muons will cross. And the next one, please. So what's expected for me is to develop simulations, and it's easier for me as I learned Gene4, and I have to take into account many characteristics, latitude, level above sea, air density, and if someone has coded before in Gen4, you see you have this file, and hopefully you can see how things are going between these layers of air density that goes and change these thermodynamic variables, taking into account trapeze, just to measure a figure that could be made of standard rock, and the detector. Okay, and the next one, please. So at the end, we can get these polar charts, and well, first was using a model, an experimental model. Then we can further we will add these simulations. This is accompanied by other research. Detector called the MERS2 detector with CERN technology, and please refer to my advisor, who is the real genius behind this. And finally, I am compelled to tell you about this experiment. It's under construction in Bolivia. It's called alpaca for the animal that lives there. And it's basically the Andes Large Area Particle Detector for cosmic ray physics and astronomy. Yeah, very large. We have to take advantage of Bolivia's high altitude, and we want to put this array like 83,000 kilometers. And we have this array of scintillators, and below them there will be muon detectors. So there's room for simulation, experiments, and more scientists. Thank you.
Okay, now Danielle.
So, good afternoon. My name is Daniel. I'm master student in the Institute of the Physics at São Carlos. My advisor is the Professor Ayon, and the title of my poster in the presentation is the Radioactive Model Reconstruction of the Galaxy Center Central Gamma Ray Sources. Basically, make a brief summary among all the high energy environment of our galaxy, like was exposed, the galaxy center region is the richest with these sources, has J1745-290 being the brightest gamma ray sources of the galaxy center. However, there is a problem because its origin is still unknown. So, in this scenario, this work is going to investigate whether the sources of gamma rays would be linked to pivotal discovered at the location. So, to do this, my hypothesis research is that the origin of the central source of the gamma rays is associated with the diffusion of the cosmic rays that depart from the galaxy center interact with molecular cloud in the central 10 parsecs. So, basically, to implement this hypothesis, I got a 3D model of a molecular cloud from Ferrieri paper. I replicated this model, and the first result that I obtained is using the diffusion equation for the propagation of the cosmic rays and the masses of the hydrogen from this paper Ferrieri 2. The gamma rays flux was calculated for two cases of sources, an impulsive case and a continuous case can be seen in these two pictures and can be talking in my poster after. And to finish, I invite everyone to go to my poster for further discussion, for deeper discussion about the results, about the hypothesis methodology, or other questions. Thank you very much.
We have time for one quick question. Or comment? No? Okay, thank you, Danielle.
Okay, hello everyone. My name is Emilce, and I'm gonna summarize the poster in a few slides. Basically, the idea is searching for sterile neutrinos, which are neutrinos that interact just gravitationally. And in this scenario, that is in the context of the three standard neutrinos with two additional sterile neutrinos, using the IceCube data. And the motivation for that is because there are some anomalies observed in some experiments like LSND and Miniboon that detect some excess in some energy range and anomalies in the reactor and gallium detectors. Why I study in this scenario, for example, is because some studies suggest that this scenario could be explained these kind of anomalies. And the reason for studying at the IceCube is because, as Irene mentioned this morning, we can take advantage of the neutrino detected passing through the air because we had this profile of the density inside the air, and this leave a signature in the 3+2 scenario in the antineutrino channel, different to the standard scenario. Yeah. Okay. So we can see in this slide basically the oscillatogram show us the probability of the survival probability of the antineutrinos from different zenith angles. This we can see the mother effect, and in this work, basically the pipeline is we introduce the parameters, the new parameter for this scenario, the new mixing mass square difference and the mixing angles. Here is an example of the element of the mixing matrix. And we solve the evolution operator through this formalism, because Hamilton formalism. And then we can calculate the number of events with the IceCube data, using the neutrino flux and the detector response for neutrinos in antineutrino detected in IceCube. And finally, this is a distribution of the number of events for the zenith angle and the energy reconstructed mean. And the next step will be computing the chi-square function. Stop. Thank you.
Hi everyone, I'm Juan Carlos. I'm postdoc at CBPF in Rio de Janeiro. And here we are presenting a novel radiative signature from binary black hole mergers. And we consider a scenario of binary black hole mergers in the vicinity of AGN disks. These environments, these astrophysical environments, have been proposed as suitable candidates or promising candidates for the origin of the gravitational waves detected by the LIGO Virgo experiment, because they have enough gravitational potential to hold a hierarchical sequence of mergers that could explain high mass black hole remnants. And also an appealing property of these systems is that the rich gas environment is suitable for producing electromagnetic feedback from these events. So we propose our model is suitable for second or higher order merger generations in a hierarchical sequence, and we argue that such events occurs outside the accretion disk because the kick that receive these remnants after the merging. These align the orbits from the disk plane. When these black holes plunges into the accretion disk, and if they produce relativistic jets and propagating quasi-parallel to the disk plane due to the motion of the kicked black hole, we calculate the extraction of disk material. This disk material that we call like a disk outflow can shine in, and we calculate, can you please go to the next slide? We calculate the emission profiles, spectral energy distribution, mostly in X-rays, optical, and infrared. And also we study the light curve profiles as a function of the parameters of the system, such as the mass of the supermassive black hole, its accretion rate, the mass of the remnant, of the merger remnant, the kick velocity, the distance from the supermassive black hole in the disk, and calculated after the gravitational wave event. This is the time delay of the electromagnetic counterpart. And more details can be found in our recently submitted paper that is, I think, is in the previous slide, this archive number, and also if you wish to visit my poster in the other room, I will be very happy to explain. Thank you.
Okay, so we're done with my talk. Now, for short talks, which are 5 minutes, and we start with Ajay.
Thank you. Thank you. So, hello everyone. My name is Ajay Sharma. I'm a second year PhD student at S. N. Bose National Center Basic Sciences, India. So these are my. This is my title of the talk. So exploring the QPOs in the Blazar light curve. It is an investigation the structural aspect of the Blazar's jet. So can you please go to the content of this talk? So actually I'm not going to talk about because Alicia has already discussed about it in great detail. So this is the outline of my talk. So first I'll talk about the objective, then whatever methodologies I have employed in this study. These are two sources, and followed by the results and the future research plans. So yeah. So like we know, the blazars are one of the astrophysical objects which exhibit rapid and complex changes in their brightness and the spectral characteristics across the multiple wavebands. So by introducing the quasi-periodic oscillation observed in the light curve, we found the light curve has some periodic patterns and variation, and the time scale of these QPOs is ranging from the days to months to even years. And by doing this analysis, we can provide the better insight into the physical processes which occur nearby in the accretion disk, nearby the supermassive black hole, or within the relativistic jets. So these are a couple of several methods I have employed to study these QPOs: Lombe-Skagal periodogram, weighted jet transform method, rate fit, and last but not the least, time series modeling. So yeah. So this is one source. It is a BLX source, and so for this study, I have used the data in this given time domain. And before the 2019, this source was in the quiescent phase, and we found that this source did not show any QPO features. So we have used this time domain because in this time domain, this source started showing some flaring activity. Yeah. So this is the light curve of this source. So as you can see, this light curve is fitted with the sinusoidal function with 3 different frequencies, and you can see the vertical line is denoting the peak of this variation in the light curve. And this work recently published in MNRS later. So if you want, you can check it out. So yeah. So now come into the variability study. So as I said, several methods I have used to study this QPO feature. So from the Lombe-Skagal LSP study, I found this source is showing multiple quasi-periodic oscillations, and these peaks are located at 0.014, 0.02, and 0.01. And this LSP study is supported by the WWZ method. And to estimate the significance of these peaks, I have used Monte Carlo simulation method to identify the significance of these peaks, and we found that these peaks have significance greater than 3 sigma, which is very good. Yeah. Change. And similar study also done for this S5 source, and I have used the data in bit is this given time domain. Yeah, change please. And we found that for this source, the QPO has the peak at 0.031 with the significance 7 sigma, which is very high, and you can see the QPO feature is lasting. It do not appear in the starting half of the time domain, but it appear after the remaining time domain, and this is the significance of the QPO peak. Yeah, change. Yeah. So apart from this LSP and WWZ, I have also done the time series modeling using two models, SERIMA and ERIMA. So basically, using the SERIMA modeling, we are trying to identify the non-linear multiplicative component in the light curve of Fermi light curve, which directly related to the curvature of the jet. So as you can see in this AIC distribution metric, in this study, we do not include any trend component, but in this study, we include the trend component. And by, as you can see, the AIC value for without any trend component is larger than the including trend component. So if you have the AIC value lower, that means your model is best model for your time series data. And yeah, please check. And this is the fitting quality. You can check several methods. Yeah. So like, so for S5 source, you can from the time series modeling, you can see the light curve also have the non-linear multiplicative component. This is the period of the QPO. And the possible scenario for this QPO is the emission from the blow, which is moving helically inside the curve jet. And for the 4FGL, we found the multiple QPOs with the harmonic relation to 3:4, and the best fit, the best possible mechanism for this 4FGL so is the Kelvin-Helmholtz instability in the accretion disk. So okay. Thank you.
Very nice work, by the way. Thank you. So, but we need to go. So, I can't read. Alberto.
Okay, so I'm Alberto. Master student in Uppsala University. Actually, this morning I presented my master thesis, but since I'm tired of talking about that every day, I choose this project I did a couple of months ago, which is about like characterizing like exoplanetary atmospheres. So not really the topic of this course, but it's what it is. So can you pass to the next slide? Basically, we have to think that when the sun, like the light of this star from another system goes through the non-transparent atmosphere of the exoplanet, we will receive like 3 contributions for the light in the spectrum. Basically, the stellar spectrum itself from the star, the telluric transmittance of our atmosphere, and finally, obviously, the planetary atmosphere. So in my project, we were working with Aronson method as an alternative to the principal component analysis. And basically, the method is capable of like computing the 3 different contributions separately. Here you can see this is the spectrum of the star, telluric transmittance of our atmosphere. And this little thing here is the planetary atmosphere, the contribution on the spectra, enhanced by 50,000. So it's like quite ridiculous to distinguish. Perfect. Here I just like compare like the 2 methods of like recuperating, like getting back this atmosphere of the exoplanet. So basically is that the Aronson method, instead of like removing data and trying to figure out what's going on there with comparing with other atmospheric models, we basically try like to model the atmosphere of the planet itself and then just like try to figure out what elements are present. And to do so, we need this limb darkening coefficient. If you remember your stellar physics class back in the day, the limb darkening is like the change of intensity through the edge of the solar disk, okay? So this is what I did. I just calculate this limb darkening for the model. Can you pass? The star that we were analyzing was this hierarchical three bodies system, main body, two little stars over there. Basically, we found like 3 exoplanets, so we were like trying to detect the component of this atmosphere of one of them. You go to the next one. To do so, we use like synthetic data from this Marx model that has like exactly the same properties of the star that we were studying, and which basically this model just like reproduces like a synthetic data of like the spectrum of this star. Can you pass? And here is like the mathematical calculation of this limb darkening. Usually people do like a numerical approach, but I just like wanted to have like analytical solution, so I did all the hard work. Basically, it's like this method of like least square minimum. So we have an approximation with this non-linear 4 coefficient limb darkening approximation. We try to reduce it from the synthetic data, and doing this nice math over here, we have like a linear system with a 4-4 matrix here, some coefficients over here. What are there for this? Here, these are the components. Basically, if you pass, we get like these coefficients for the K band. We were expecting like a linear trend. We didn't find it. So I just like, if you pass to the next one, I just like try to plot like several like polynomial. You can see that they, after like order 2, they basically behave the same way. So just like for simplicity, we choose cubic formula. You pass. And, no, actually, no, before. We here even find like these little outliers here and there. And now if you pass to the next one, we can see that they actually fall into the regime of these like absorption lines. This is like calcium 3. There's like a sodium 2 over here and some CO composition. And this is because of the modeling of the star, like the synthetic data. And basically, can you pass? Basically, is that this Aronson method is like, I think it's a better approach than the principal component analysis to get like this spectra of the atmosphere of an exoplanet, because we don't remove data, but we actually recover it. We found like this approximation of the limb darkening needed for the model to work was not linear, but polynomial of like order 3 fitted approximately good, like more or less fine within the errors. And the presence of the outliers was like located at the strong absorption lines due to the way the synthetic data works. Yeah, maybe it's like too specific, but it was a good work. The thing is that for future works, we were like aiming to study like the wavelength dependence on other bands that were not the K band, and also like modeling different stars to see if like the same method could work like to detect these stellar atmospheres. And yeah, that was it. Thank you.
Perfect. Okay, thanks for that talk. Now, Anastasia.
Okay. Hello, everyone. My name is Anastasia Baluta. I represent Lomonosov Moscow State University. My work is basically about the environmental effects and its influence on type 1a supernova standardization and cosmological analysis. So it's a collaborative work with my scientific supervisor, Maria Puzhinskaya, and our colleagues, Philippe Rosnet and Nicolette Pauner. Next slide, please. So type 1a supernova are widely used to measure distances in the universe. But despite the recent massive progress in supernova standardization, we still see some intrinsic dispersion in the luminosity on the Hubble diagram. And it may be connected with So it may be done with some environmental effects and some environmental corrections. We use one of the most popular standardization models. It's called SOL2 standardization model. It contains two parameters. It's a stretch parameter, which is correlated with the width of the light curve, and it's a color parameter. Also, there is a gamma parameter, and it is responsible for the host stellar mass. And by the host mass, I mean the galaxy in which supernova exploded. But even after all this standardization procedure, we still have some intrinsic dispersion left. It's about 0.1 magnitudes. Next slide, please. Okay, so we use the Pantheon sample. It contains more than 1,000 type 1a supernova. And for 330 supernova, we have identified morphological types of hosts. Well, hosts are basically divided into two types. They are early type galaxies, and there are 91 supernova, and late type galaxies, around 240 supernova. Also here on the right, you can see the plot from Punjinska and colleagues, and there showed the correlation between host morphology type and the value of one of the light curve parameters. So it's a stretch parameter correlated to the width of the light curve. And you can see for the supernovae in early type galaxies, the value is much lower. Next slide, please. So basically, what first thing that we do, we made a Hubble diagram feed for all of our more than 1,000 supernovae. We have four parameters, a cosmological one. This one is connected with the stretch parameter, with the color parameter, and this one corresponds with the correction for the host stellar mass. So what we wanted to do is we wanted our values to be as close as possible to the values from the original paper of Skolnick. And I think we did quite a good job. So here, what we did next is we explored the possibility, so the influence on the two of subsamples of supernovae. The blue ones are supernovae in early type galaxies. The red color represents supernovae in late type galaxies. Also, there are the green stars, and they represent pretty much these results. So on this joint plot, you can see lots of parameters, alpha, beta, gamma, the magnitudes, and for two of the subsamples of supernovae, we see that there are shifts in these values. So there are shifts in magnitudes, shifts in alpha values, beta values, and I want to stress that here we have some environmental correction. So the gamma parameter is it. So even with these parameters, so with the environmental correction, the standardization is not completed. So we put the gamma parameter to 0, and we did pretty much the same thing. And so here we have no environmental correction, and still the standardization is not completed. Here on the slide on the right, you can see the residual plot. The residuals is pretty much the difference between the theoretical distance modulus and observed distance modulus, and we want this value to be equal to 0 for all the dots, but it is not. So now we're heading back to the summary. On the basis of the Pantheon sample, which contains more than 1,000 type 1a supernova, we explored the influence of different environmental parameters of host galaxies on the standardization procedure. And we showed that even with some environmental parameters, such as stellar mass of the host galaxy, the standardization procedure is not yet done well. We showed that the standardization procedure needs to be done because even with no environmental correction, the standardization is not complete. And so we claim that there should be some standardization, some environmental parameter, and we want it to be actually the morphology, but that's what for our future work. So we want it to be there. That's it. Thank you.
Thank you. So, Caroline. Oh.
So, hi everyone, my name is Caroline. I'm from CBPF, and my project is about neutron stars and modifier theories of gravitation. I'm working with Raisa Fernandes from OFI and also Felipe Tovar from CBPF. Can you pass, please? So, our goal is to help with astrophysics tests of GR and also modifier theories of gravitation. And to do so, we are building a code in Python, which is pretty much inspired by RNS. You may have heard of it, but it's basically C code that allows you to calculate the equilibrium configuration of rotating neutron stars. So we are basically expanding this idea to modifier theories of gravitation. And well, I'm not gonna be able to talk that much about neutron stars, but there are some summarization of the idea. So for static neutron stars, we have this metric, and to define the equilibrium configuration, we have a set of equations, which are the equilibrium, the equation of states, the equilibrium, the hydrostatic equilibrium, and also two Einstein field equations. Okay, so this is a classic plot of mass radius using three different equations of states. I used my code to reproduce it, and please, next one. So in the case of slowly rotating neutron stars, which are the stars with this magnitude of angular velocity, we can calculate the equilibrium configuration using an expansion in the angular velocity up to the second order. And what we do is basically feed these equations with a background information, which is basically an aesthetic neutron star. And so we feed these equations, and then we get the uniformly slowly rotating. Of course, this is done numerically. So, well, that's it. Please. So here are some plots again. We have the inertial momentum and also the ellipticity of the star, to different types of equation of states and different values of angular velocity. And so for the last case, which are the most interesting one, is the rapidly rotating neutron stars, which is basically more complicated because here we have sets of differential partial equations, which are much more difficult to solve. But okay, as I said, we already have a code in C that solves it for us numerically. And well, the idea is basically to calculate several iterations until you reach the desired angular velocity that, well, you want for the star, basically. I don't think your face is not really good. Okay, so please. Yes, please. So as I said, we are still I don't think I said it, but okay. Oh, thank you. So as I said, we plan to work with modifier theories of gravitation, but we did not get there yet. We are in GR still. Our results for uniformly slowly rotating are in good agreement with the one presented by Hartel. And as I said, we are finishing GR, so we are still testing the rapidly rotating case. And then we are going to introduce the modifier theories of gravitation in our code, and then get some, I don't know, some properties of stars, some results that will contribute to astrophysical tests of GR and modifier theories of gravitation. So using gravitational waves and etc. Yes, that's it.
We have time for one question, if anybody wants to ask.
Oh, no. I'm really curious. So do you have in mind any tests of modified gravity that you plan to do?
Yeah, so no, we didn't get there yet. It's the second phase of our project. I'm still in the middle of my master's degree, so we are still in the middle of the project. So I can't have the answer now, but yeah, that's it. We are planning to have some, of course, relevant results, right, about this. But I'm not gonna have the answer like properly because I didn't get there yet. So I'm sorry. If you ask me some months, I don't know, next year, I'm gonna have the answer.
Or during next coffee break. Okay. Next up is Dia. Dia. Ah, pode desligar a luz?
Okay, great. Hello, everyone. My name is Dija Delgado. I'm a PhD student at Harvard University working with Carlos Argüelles, who's coming in uh, next week. So I'm going to talk to you about one of the many things that you can do in neutrino physics and with IceCube. So I'm going to be talking about one of my projects in dark matter neutrino scattering at the Galactic Center. No. Just next slide. Thank you. Just as we heard yesterday, thank you. There's some strong motivation for dark matter annihilation closely related to the WIMP miracle. And if we can see or expect dark matter annihilation, then we can also expect dark matter neutrino scattering, so therefore is implied. Next slide. So what we're looking is for dark matter neutrino incoherent scattering. So it's been shown that the neutrino flux follows an isotropic distribution. And somewhere along in space, time, our neutrinos would interact with dark matter. In this case, I'm interested in the galactic center. And these neutrinos would get attenuated, so you get less neutrinos coming for that particular direction. So this results in an anisotropy of the neutrino flux. All right, so these interactions can happen in many ways. So I'm just gonna show you 4. And by no means this is all of them. There's a lot. When you give physicists time, they get very creative. So starting from the left, we have scalar mediator, scalar dark matter, and below them is how they scale with the neutrino energy. Next, we have scalar mediator, fermionic dark matter. Third one is vector mediator, fermionic dark matter. And finally, we have fermionic mediator and scalar dark matter. So I'm gonna show you something about the second and fourth model because I like to call them the inverted cousins. And they also have the same scaling in neutrino energy. So it would be interesting to see how they change. Next slide. So here, the attenuation effect that we can probe or look into is this attenuation effect that we call survival probability. Which is a ratio between the attenuated neutrino flux and the isotropic flux. So for now, we are considering a single power law, but we can also consider like broken power law and get even more details into it. So on the left, for a given parameter, dark matter parameter like coupling, mediator mass, and dark matter mass, and for this model particularly, the fermionic dark matter scalar mediator, we can show the survival probability, and you can very barely see anything. So we have to zoom in, and what we see is that at the galactic center, you get a 92% survival probability. So almost all the neutrinos coming from the galactic center are coming through and not interacting with dark matter. But when we see the inverted cousin, we see that we have a 40% chance of getting those neutrinos back from the galactic center, so they are getting attenuated. Next slide. All right, so the analysis is quite simple. You just have your IceCube data, your neutrino energy, and your event coordinates, and you feed that into your bin likelihood. And then you have your model that would depend on your neutrino sources. So you have your astro neutrinos, which are the ones that we're interested in. So that's our signal. And then we have our common backgrounds, which is atmospheric neutrinos and atmospheric muons. Then you have to take into consideration your dark matter properties. So as we heard yesterday, there's many different dark matter profiles, and we have to tackle it, or you have to integrate it for the galactic center, so it becomes a column density. And then finally, you can add your new physics. So this is when we can also get really creative. And this is where your dark matter parameters come in. Next slide. So this is what it would look like. We're interested in formulating this Poisson likelihood and then computing a test statistic between your dark matter parameters or hypothesis and your null hypothesis. So it depends on event coordinates, dark matter parameters, and also some nuisance parameters, many others that I'm not including. But you can separate your likelihood into your signal, which is our extragalactic astrophysical neutrinos that follow a power law spectrum. And then that would depend on your attenuation effect. And then you profile over these nuisance parameters, and it looks good. And then you have your background, which in this case is atmospheric neutrinos and muons, that you scramble over. In this case, I'm still using Monte Carlo because you have to unblind and there's these procedures. But you scramble your data over right ascension so that you can have this sharp peak or smoking gun signal over your background. Next slide. So this is what the results would look like. So this is a test statistic. That's the color here, or delta log likelihood. So you can do these type of plots for many different parameters. So here I'm showing in the y-axis the coupling, and then the x-axis the dark matter mass. So what you can see is that for certain low mediator mass, your excluded regions, which is in black, don't really change. But as you increase the mediator mass, you're no longer sensitive in this particular model, which I did not mention, but it's fermionic dark matter scalar mediator. And then you can go to the last slide. So essentially, we do this for a bunch of parameters, for a bunch of models, and then we also do comparisons between what we call inject recovery, where instead of looking at no dark matter case, you fit one specific dark matter case, and then you test it all around. So that is what we've done. So any questions, you can just come to me.
All right. And now, Ezequiel Zubieta. All right, so here.
Hello everyone, I'm Ezequiel Zubieta. I'm a PhD student at the Argentine Institute of Radioastronomy. And I will tell you about the pulsar monitoring campaign that we are performing from the Institute. Next one, please. To begin with, let's talk a little about pulsars. Pulsars are highly magnetized, rotating compact stars, and they emit electromagnetic radiation out of their poles. Given that the rotation axis is not aligned with the magnetic axis, when we observe pulsars, we observe regular pulses, which look similar to a lighthouse. And these pulses correspond to the period of the pulsar. Next one, please. So the technique that we use to study pulsars is quite simple. The idea is to register the time of arrival of the pulses, also called TOAs. And on the other side, we develop a timing model capable of predicting the time of arrivals. So then we calculate the residuals, which are the difference between the predicted time of arrivals and the observed time of arrivals. And if our model is accurate, residuals should be clustered around 0. But if our model is not accurate, residuals will follow a pattern, and we can use that pattern to develop a better model. So our idea is to use this technique to mostly study two things. On one side, to collaborate with the study of gravitational waves, and on the other side, to collaborate with the study of equation of state of superdense matter. Next one, please. So when a gravitational wave passes through space, it modifies the time of arrival of the pulse. So it will modify the residuals that we are seeing in the order of the nanoseconds. So if we analyze the correlation between pulsars, we can detect the low frequency gravitational waves. And this is really cool because it is an excellent complement for the LIGO detectors and LISA detectors because they can't reach such low frequencies. Next one, please. So at the Institute, we are following in particular this pulsar, and our residuals are of the order of the microseconds, so we still didn't reach the accuracy of nanoseconds to be able to detect gravitational waves. But we recently acquired new acquisition models, and we are working on our timing model to have more accuracy. And we are given that we are in Argentina, we are in a prime spot to be able to monitor, for example, this pulsar that it cannot be monitored from other places. So if we can add this pulsar to the nanograv collaboration, we could improve their sensitivity in that part of the sky, even in a factor of 3. Next one, please. On the other side, we study glitches. A glitches is a sudden spin-up in the rotation frequency of the pulsar, whose cause is still not clearly understood. So we look at pulsars that have shown glitches before, and in particular, we have already detected 6 glitches in just like 4 years. So we hope to use these glitches to understand what is going on inside the neutron stars, because this sudden increment in the rotation frequency is probably related to the equation of states of matter inside the neutron star. Next one. So that's all that I have to say. Just to summarize, we are working on our sensitivity and our timing model to be able to collaborate from Argentina with the detection of gravitational waves. And on the other side, we are monitoring pulsars that have some glitches to be able to collaborate with the study of the equation of state of superdense matter. That's all.
Have time for one question. No? You should sit here.
How long will you take to arrive to the accuracy of the nano frequency?
Well, we are not completely sure of the time, but we are on the microseconds right now. And we just acquired these new acquisition models like 1 month ago, so we are testing it. We hope that it will improve our accuracy in a factor of 10, so we will be close to 100 nanoseconds by now, and we have to keep working on the timing model to be able to have more accuracy.
So 1 year time.
What?
1 year time.
Yeah.
Okay, thank you, Ezequiel.
Thank you.
Now we have Fernanda, Maria Rodriguez.
Hello, everyone. I want to talk briefly about neutrino mass ordering problem. Please. Okay. So, as we know, neutrino mass hierarchy has not been completely determined, but there are some possibilities. Like here in this first column, we see the normal order is illustrated, and in the second column, we have the inverted order. And one way to investigate this phenomena is using oscillation probability. So let's look for an example related to this problem. And this plot here is a B probability plot for a mu neutrino going to an electronic neutrino, and for a muonic antineutrino going to an electronic antineutrino. These dashed curves correspond to results of the experiment NOVA only, while the solid curves correspond to the combined results of NOVA and 22K experiment. The colored dots are the best fit for the charge parity phase, and the black dot is the statistical result. And what we see here is that when analyzed separately, both experiments prefer normal ordering, but their combined results prefer invert ordering. Another interesting question related to this combined data of these two experiments can be seen in this plot of the square of the sign theta 23 to the charge part phase. And what we see here in the part of normal order is that the best fit for 22K is placed in the region excluded by NOVA with 9% confidence level. So the question is, can this issue be a sign of new physics? Well, in order to investigate this problem, some colleagues from University of Campinas and I investigate the possibility of this be a sign of physics behind the standard model. For this, we use an effective field theory approach and consider a non-standard neutrino interaction affecting the neutrino production, in which we obtain this equation here for the oscillation probability. So we simulate again these events, but now in the presence of this non-standard interaction. And here in the same plot, we can see how the ellipses had changed, and that now in the presence of the n side, either when analyzed separately or in the combination, there is a preference for normal ordering. And again, in the second plot, now we can see that the curve for the allowed region for the NOVA experiment has changed. And so now the best fit for T2K is now in accordance to the NOVA with 9% confidence level for the normal order. We can conclude so that determining the order of neutrino masses plays a key role in understanding the physics of flavor, and uncovering this information could pave the way for unlocking the interconnections between lepton masses and mixtures, and that non-standard neutrino interaction could have implications in neutrino oscillation probability. It could change constraints, have consequences in matter effect, and alleviate tensions between experiments as a consequence of new physics.
Any questions for Fernanda? Okay, Alicia.
And have you tried using data from other neutrino detectors, or?
Not yet, because we are specifically trying to understand the tension between these two experiments, but we are looking for another experiment also. Thank you.
Guillermo.
Hello everyone, I'm Guillermo Gambini, and I'm here to talk to you about the possibility of dark matter signature in really neutrino searches. Next slide, please. Yeah, so we know, we have seen this pie chart of the energy content of the universe, where we have, you know, visible matter, and dark energy. Okay. Okay, so everyday matter, as we know, is like, you know, stable particles like electron, protons, but there are also unstable particles like muon, tau, and neutron, etc. Right? And these guys also make they put together to make atoms, right? Which could also be unstable. If the number of neutrons, for example, is larger than the number of protons. Next slide. Yes. So what about dark matter? Yes, dark matter can be a single stable particle, which is boring, you know, but it could also be new fermions, gauge bosons. It could also be also form new dark mesons and dark baryons, right? Yes. So yeah, and maybe this fraction of the dark matter can decay into dark radiation. Here we can see that in this cartoon that depicts the evolution of the universe, you know, from the Big Bang. If dark matter is allowed to decay after recombination, right, until today, it is about 4%, no, 3% is allowed to decay without having any problem with observations like CMB, for example. And here you can see constraints on this decay rate into dark radiation, any dark radiation, right, as a fraction of the unstable component. Next, please. Thank you. So the proposal here is that this dark radiation may be neutrinos, right? So maybe dark matter can decay into neutrinos. Thank you. Yes, the process will be like this one shown over here, right? And if the dark matter is cold, the energy of the neutrinos will be about half the mass of the dark matter. Thank you. Yes, the momentum, you know, after the evolution of the universe, the expansion of the universe, when neutrinos lose energy, will be reduced by, you know, the redshift. And for these benchmarks that I'm showing you here, for example, for a KeV dark matter, right, that was produced near, for instance, after the CMB, right? This dark matter that would be KV, this neutrino would be KB, now would be like EV, an EV neutrino. And if we have a 1 GeV dark matter, unstable dark matter candidate, that decays into neutrinos near, for example, the time of neutrino decoupling, this will be milli EV neutrinos today. Yes. So this is just basically the parameter space of this model would be like the redshift of production and the mass of the unstable component of the dark matter. Neutrinos that have been extensively studied in many experiments and observations around the world and outside the planet could be classified maybe like in solar neutrinos and terrestrial neutrinos, also from supernova neutrinos, reactor neutrinos, and then atmospheric neutrinos, and then one stop in the next one, which is neutrinos from the active galactic nuclei. And these guys are all relativistic neutrinos, right? But if we go to the next one, so the Big Bang neutrinos, no, not that one, the next one, please. Yes, from that Big Bang, okay? These guys could be non-relativistic, right? You can see. So the proposal is that maybe in this part over here that I know is not explored, there could be neutrinos that come from dark matter decays, and if they are also non-relativistic, they could also be present in future searches for Rayleigh neutrinos that are non-relativistic, in like Ptolemy-like experiments. So in conclusion, the dark sector could be richer and more complex than what we think, right? And dark matter could be multi-component. We don't know that, which would be interesting, than just cold relic density. An example that could work is the majoron, for instance, could decay into neutrinos, and these guys could be, searched for, found in future searches, that have been proposed, like Cavendish-type torsion balances or Ptolemy-like experiments that were, so people are been working on. So yeah, so this is work in progress. Thank you.
Okay, now, Josiel. It's a hands-on?
No. First. Okay, thank you very much. I'm Josiel Mendonça from the Federal University of Rio Grande do Norte, a PhD student in the last year. And in the short talk, I'm going to talk about our developed software, the GW DALI. That is a Fisher metrics-based software to estimate standard sighting parameters beyond Gaussianity level. That is, you are not using the standard method to perform parameter estimation, but use approaches of the likelihood of gravitational waves. So next one. So it's a simple software which you can install via pip. It is available in the PyPI, and the documentation in the site. Read the docs where you can see all of the details about the parameters of the gravitational wave source, the parameters of the detector, and so on. It is very simple to use. Next. So the parameters of the gravitational waves that we're using in this software is the 15 parameters for circular orbits in a circular orbits of these binaries related to the black hole. Where the left column you have the intrinsic parameters of these binaries, the mass of the objects, the spin components, and the right side we have the extrinsic parameters, the right accession, the inclination, the sky position of the source. We have the iota, that is the inclination of the binary with respect to the line of sight between us and the source. Psi is the polarization angle. And we have a T-coal and phi-coal, that is the coalescence phase and the phase of the coalescence. So the way that we use to call these parameters is define a simple dictionary of the Python, where you use one of these keys and setting the values of your parameters. And the units you can see in the documentation for more details. Next. For the sensitivity curves of the detector that you can use is the current one for the second generation detectors, the advanced LIGO, advanced Virgo, and Kegra, as well as the third generation detectors, the Einstein Telescope and the Cosmic Explorer. Next. So you can, in this software, you can model your detector as well as you want. You can define the coordinates of your detector that is not available in other softwares. In my software, you can set the coordinates. You can set also the orientation of your detector that is not available in other software, but in my software is available. You can also set the shape of the detector. You are not restricted to use L-shaped detector. You can change the opening angle of the arms of your interferometers, and you can also change the sensitivity of your detector. It's amazing. Next slide. So the way to perform the parameter estimation. The standard way to perform parameter estimation is using the standard likelihood of the gravitational waves, where you have the capital H, that is the output of your detector, the data, and the small h is the template that you use it, and the theta is the set of the gravitational wave parameters that are called before the 15 parameters, or you can use any number of detectors that you want. You are not obligated to use all the 15 parameters as free parameters. You can choose 3, 4, 5, or any one. So next slide. So the Fisher approach is basically you get the logarithm of the likelihood of the gravitational wave, expanding the tail expansion up to the second order in derivatives, in the displacement from the best fit parameters, and the coefficient of this expansion is the Fisher parameter, this Fisher matrix, and the rest of the Fisher matrix is the covariance matrix, for which you can estimate the uncertainty in the parameters of your gravitational waves. Next slide. So the DALI is an algorithm that was proposed in these two references there in red, for which they expanded the logarithm of the likelihood, not only up to the second order in the displacement from the best fit parameters. They go beyond to the third, second order in the derivative of your template. Next one, this is called the doublet DALI. In the order expansion, go to the third order in derivative of your template. That is called a triplet DALI. So we use this, my code is available to use the standard method, the Fisher approach, the DALI doublet, or DALI triplet. Next slide. So it's very simple. You can call the function of my GW DALI software is basically a simple function where you define your detection, your free parameters, the detector that you want as a set of parameters, not restricted to only one detector. You can set multiple detectors in the way that you want. So for more details, you can check the documentation for installation. Thank you very much.
Hi, everyone. Nice to meet you. I'm Laura Villegas. I'm from Universidad de Guadalajara, Mexico. And my topic is about gravitational waves from core collapse supernovae. Next slide, please. Okay, this morning we saw many of these things, principally in this part in the core collapse process. I tried to understand everything about that. So it's a very difficult topic because we have many areas of the physics involved in this part. I search from stellar evolution until the generation of the gravitational waves. So we saw that the massive stars evolve we know the massive stars evolve different than the small ones. So in this part, most of the life of the stars is passed in the hydrodynamic equilibrium. So consuming his hydroxin. Sorry for that. And the nuclear reactions convert this hydrogen, hidrógeno in Spanish, until helium and so on, until have a nuclear iron core. So when we reach this core, this iron core, we can separate in two parts the core, external and internal. The material external falls to our center, so the collapse begins. In the center of this core, we have a protoneutron star, so the material when falls, the material shock with the protoneutron star. So this process we call core bounce because it's like a bounce, literally a bounce. So in this part, when the core bounce occur, the gravitational waves sorry for, I lost the word. Okay, the gravitational wave forms. So this is the morphological of the gravitational waves, only for the rapidly rotating core, okay? The Abdi-Kamalov group, they do many numerical simulations, consider all of the physical parts, and principal, the rotation. So it's very important because we have the angular momentum and we can separate in three parts this signal. In the core bounce, the PNS oscillation and prompt convection. So we can classify these signals with slow rotating, rapidly rotating, and fast rotating. This, and they define this parameter beta like the relation between the cinematic energy entre between, thank you, between the gravitational energy. So, okay. For us, it's very important because we use a frequentist methodology to calculate analytically the error of the maximum likelihood estimated. We use asymptotic expansion for calculate the estimation error. So in this part, we use the simulation signal, and we can do analytical model. This is a equation only for the core bounce, because the core bounce is the part of the deterministic. So we can do anything about this fluctuation. So with this equation, we searched the estimation error of the covariance. So the next one, please. And the estimation error, we calculate with these equations for the first order of the variance and the second order, and we have the relative error of the estimation of beta, of the parameter beta. So we define this area like a confiability region. So the estimation, it's, okay, when we calculate the value of beta, and this value found in this region, it's a good estimation. So this is the plot. And also we calculate the signal noise ratio. So this method we repeat for the power spectral density to LIGO, to Einstein telescope, and to Cosmic Explorer at the different distances.
Laura, you need to conclude. You're way beyond time.
And that's it. Thank you.
Sorry about that. So, last one of the day, Leandro. Oh, here you go.
Well, hi everyone. First of all, thanks Raul, Cecilia, and the other organizers of this amazing school with such high quality lectures. My name is Leandro Avaro. I'm from Argentina. I'm in the second year of my PhD, and my advisor is Gustavo Romero, who some of you may know. And I'm going to talk about black hole clusters in supercritical AGNs. But before, I want to show you the main topics of my PhD and pay attention to this second item here, because I work mainly with supercritical or super Eddington, is the same, accretion regimes. Basically, the idea is that we have a black hole that it's accreting at very, very, very high accretion rates. So one thing that happens in these systems is that a wind is ejected, a very powerful wind is ejected from the accretion disk. So the disk is self-regulated to the Eddington accretion rate. And that wind is going to interact with the things that are in the environment of the black hole. So many things are going to happen. In particular, we can have some shocks over there. So this is mostly related to what Alicia and Brian have been talking about in their lectures. And before I talk about clusters of black holes in AGS, I just added this slide yesterday because we saw that there are some systems called gamma ray binaries, and I want to add another type of gamma ray binary to that list that we saw. These systems that we call supercritical colliding with binaries in a recent work. And the idea is that we have a stellar mass black hole gravitationally linked with a star, and the star has its wind, and the black hole, as it is supercritical, also has winds. So the winds are ejected from this inflated supercritical disk, and the winds are going to collide, and we have shocks here where particles can be accelerated and non-thermal emission can be produced from radio to gamma rays. So now going to the very topic of this talk in my remaining 7 seconds. I'm going to talk about clusters in clusters of black holes in supercritical AGNs. This is a current work that we are doing with my advisor, Gustavo. And the idea is that we have a supercritical, supermassive black hole in the center of a galaxy. And as it is supercritical, the disk is going to eject very powerful winds. So these winds are going to interact with a cluster of stellar mass isolated black holes that should be in the center of galaxies. So there is a work from the year 2000 in which the authors have shown that tens of thousands of isolated stellar mass black holes should be in the center of galaxies. So the question is, what happens when the Asian winds interact with the stellar mass black hole? Because we cannot prove that these black holes are there. So the basic idea, and this is the final slide, what we are thinking is that maybe the Asian wind that comes from the center of the galaxy, of some galaxy, interacts with the stellar mass black hole, with some isolated stellar mass black hole, and via the Bondi-Hoyle-Littleton accretion regime, that is a cylindrical accretion regime, the matter forms a small accretion disk around this stellar mass black hole. So we don't know if this system exists. We are trying to find out what, if this really can happen. But the idea is that the stellar mass black hole is capture matter from the Asian wind and forms this small accretion disk. And if we have an accretion disk here, we can have also a shed. So if this actually happens, we can have tens of thousands of stellar mass isolated black holes that are orbiting supercritical AGNs that are illuminated by the AGN wind. Okay, so we will have like small lighthouses pointing in random directions, and maybe we can have non-thermal emission produced in the shed. So this is what we are doing now, and we like to put names on new things. So we called supercritical colliding wind binaries the previous system that I have shown you, and we have called these systems non-stellar microquasars, because in a microquasar we have something like this, but with a companion star. And here we don't have a companion star, we have just the Asian wind. So this is the basic idea. We can talk about it if you want to later. Thank you.